Hello, good morning to lesson 11 of CE 5361. And so I will start kind of slowly. It's Tuesday, July 16th, 2020. And I know that because I had to get up early today to take my beasts to the cat doctor for some repairs. I'm looking out my window in my backyard. Looks like it's a nice day. So the stated topic for today is surface runoff mechanisms. If we stuck with just that, it's a really short lesson because this is as far as I got putting these together. We've actually seen these in the infiltration portion of the class last week, and the intent would have been to describe each of these mechanisms in greater detail. So I'm not going to do that today. What I'm going to do instead is complete example 2 of the introduction to SWMM, compare it to HMS, and I got what I think is smart. I've preloaded a lot of that on the demonstration machine for myself. And very good. So for the so John and Superada, you just joined us. I was stalling until you got here, so you haven't missed a thing. What today's lesson is going to comprise is it's supposed to be these 3 topics, and I don't have any additional material for them. These were discussed briefly in the infiltration portion, and my intent was to go into them deeper, and the purpose is to segue into unit hydrograph theory, which is a transformation mechanism. And we'll do that tomorrow. That's all prepared. So what I am going to do for the rest of the time today, and I hope not to take an hour and a half, is to complete the SWMM example, example number 2, show some additional features of that program, and then compare it to HMS of the same problem, and that will complete what I consider the software introduction. And then we'll go for the remainder of this week in fairly elaborate detail on a transformation model called unit hydrographs. You may have had that in your other classes. Much more in the underlying theoretical aspects of it. Unit hydrograph theory is a probability estimation modeling theory, disguised as something else, because in the past it was found if you stated probability and statistics, that could dissuade a lot of people from studying it further. It's really just a particular functional behavior, and we'll examine that in some detail, and it's a useful tool. But today we will complete the SWMM example. So I'm going to disappear that, hit save. You now see where I get all my cool pictures from, the mighty internet, everybody's favorite place. And make sure I'm in the right web browser. There it is. Okay, so the real lesson 11 today is going to be the continuation of lesson 10. All right, so with no further stalling, let me go to that. I've already connected to the VNC server to desktop number 1, which is the development one. That's different than the 5 you all have. It's on the same machine, but this is a different account than the 5 you have access to. And I will wait for Ian to connect. It should be showing a... There he goes. Okay, so Ian, you just joined us. You haven't missed anything substantial yet. What I did was introduce what today's topic is. It departs from the stated syllabus in that I'm going to essentially complete lesson 10 from yesterday is what I'm going to do today. And there's some other material that you can review the video on. None of it's urgent yet. I assume you all got the email last night that mentioned that exercise set 2 is available and ready for you to complete. It's not very difficult, so get to it as soon as you can, because I think I set a due time on Friday. The other thing is lessons 10, 9, 8, and 7. I think I got those coded so you can actually look at them on the server and receive, for lack of a better word, acknowledgement that you looked at them, which I use for my, quote, roll taking. So again, when you have some time in the next day or two, complete those. Don't particularly worry about whatever grade it assigns you. On most of those, I'm doing overrides. So all I need to do is detect that you looked at it, and then I just override it to a 100%. All right, well, that's enough administrative stuff for today. And so what I've done, everybody, is I'm on the HydroShare site, and here I'm looking at the SWMM models, and I've created a directory for example 2. Currently, there's nothing in it. You see that some of these are bitmaps and some are JPEGs. There's one PDF, which we established last time, SWMM can't read. And here's our HEC HMS model from Ash Creek from lesson 9. And I have it to these two locations because I'm going to attempt to make a SWMM model more or less agree with this. Probably not going to be able to get a super good agreement, but I'm pretty sure I can get the magnitudes correct. And again, we can, at that point when that's done, we can comment on the differences between the two softwares when we are examining the same situation. And the big question I'm leaving unanswered is which software to choose when. So I've got SWMM up and running already, and I want to make a project. I'm going to choose new, and we're now in a new project, and let me just put a single element on it to create the project. So we're going to have an outfall, and that's good enough. And the other thing I want to do is I want to see if I can load in a file. So I'm choosing View from the menu, Load, and now I'm going to go looking for backdrop images. So I have bitmaps, which are huge files, and I have JPEGs, and it looks like it's going to let me try a JPEG. So I'm going to choose the shaded relief because I think it's pretty cool. And let's see what happens. Oh, that's really amazing, actually. Well, unfortunately, it's rotated, and I'm not sure if that's something I can manage from within the SWMM software. But it's relatively trivial to rotate an image external to a software and then load it in. What's important is we now can use the map to help us construct our model. In this case, it's going to be really silly. And I think if I click on this globe, oh, that's what that does. I thought it let me turn off the view monitor. I'm going to unload the backdrop, and I want to check on something. I don't think these backdrops are georeferenced, but let's find out. So that was shaded relief as a JPEG. Let's see what the topographic map looks like. Now this one, actually that's not bad. It's pretty darn close. So here's a topographic map of the same area. So this is a feature of SWMM that I don't think HEC HMS has an equivalent to. So did somebody just join, or oh, that Superada just lost her connection again. Let me get my chat up and running, so in case she wants to get a hold of me that way. Okay, so Heck doesn't have a really convenient way to load in pictures in the background. It has a way to load in files in S3 and a couple of other DXF and a couple of other formats. And you can, in theory, make something that they call a map file, which is just a list of coordinates that it will use. I tried that earlier last week, and I'm either making the file incorrectly, which is possible, but I doubt it, or it's a feature that no longer works in Heck HMS, and they haven't bothered to remove it from their user manual. All right, so neither here nor passing. The important thing is this is just a picture, so there's no geographic referencing to this picture unless we turn that on and we can identify corners, and that's fairly elaborate with SWM. But what the picture allows us to do, or is helpful for us, is it gives us ability to kind of pictorially manage our model construction. So I'm going to put back the shaded relief, view, backdrop, load, grab the shaded relief map, do it as a JPEG, and we'll work on it twisted sideways. Okay, so there's our outfall. Good, let me move it. So I'll move a little bit downstream here, mostly just for pictorial reasons. And now let's suppose I want to create a subcatchment. So I'm going to treat this whole thing as a subcatchment. And here's where the drawing tool comes in kind of handy. So as of now, the computer program has no idea how big this area is, and it won't when I'm done drawing. But for presentation to clients, people that are going to use the output of your hydrologic analysis and science, this is pretty useful because it gives you a way to communicate visually what we're trying to do. And so there I've just drawn the backdrop. All that is a blob. Right now, the computer thinks that that blob is 5 acres. Okay, I seem to recall earlier when I measured this, it's 6.9 square miles. Let's take a look at our SWM model because that information is already there. Oh, we're in SWM. I meant Heck HMS. 6.92 square miles. So we'll give it the same value in SWM. So now we have to figure out how to represent 6.92 square miles in a computer model that expects things to be in acres. That's reasonably straightforward to accomplish because 6.92 multiplied by 640 acres per square mile would give us the number of acres of the watershed. I can't do that in my head, and I don't have a calculator handy. So let's see if I can use the tools that are built on board. We do have RStudio available. So at the attempt of crashing my whole remote server, this is pretty lightweight. It should be able to handle it. That's good. So I want to do 6.92 times 640. So 4428. We'll copy that, shrink that, bring SWM back to the front, hit paste, and save it right now. And we'll just call this Ash Creek single catchment. That's a note to myself, because later on we're going to take advantage of both these tools in that we can break that watershed up into smaller pieces that we have more understanding of. And now we have to decide on what width to make things. And I'm going to check my email to see if Super Rod is trying to get a hold of me that way. Nope, she must have had a internet failure. A lot of that been going around lately. So now I want to figure out how to take 4,400 acres and represent it a reasonable amount of width. We should quit doing that. If I do the save project, oh, it never got the input. Yeah, so these cobbled together softwares aren't perfect because of the way it's being run on a shared server. It's still pretty incredible, actually. We have to put the width of the overland flow path. So I'm fairly familiar with watershed. Let's go ahead and bring the view back up. Well, I'm just going to make a number up, but not willy-nilly. Topographic. So let's see if we can get an idea of what these scales are. I know those are in meters. 2,000. Okay, so each of these blocks is 2 kilometers. So if we just sort of call this distance here a representation of, say, a reasonable average width, that's like 2, 4, that's 5 kilometers, which is 3 miles. So 3 times 5 is 15,000 feet, give or take. I'm going to use that value as an approximate width to get the length. I'll leave the slope alone, although that particular watershed is steeper than 0.5%. I'll leave everything else as defaults for the time being. There we go. Welcome back. Welcome back. Figured you had some network problems, and like I said, there's a lot of that going on. So initially, this is our watershed, and we have to give it an outlet, which I think is going to be outlet 1, and at the risk of crashing all of this, go ahead and exit from that. And here's why I want to turn off the backdrop. So we have successfully connected that blob to this outlet. So as far as the software requires, we've established the hydraulic connection. If we can get everything else right, we should be able to get a model to run. We'll leave the backdrop off for the time being. We'll incorporate it when we need it. We'll go ahead and add a rain gauge because we'll need that. And the rain gauge can be put anywhere. I'm going to stick it, actually I'm going to move it way up here so it's kind of outside the picture so we'll be able to find it when we need it. And we'll return back to it, and back to this subcatch it, and we'll go ahead and identify the rain gauge. So this is very much morphologically the same as the HEC HMS model of the same region. There are some substantial differences in that how the rainfall and runoff rainfall is converted to runoff in SWMM. We also need to presumably use the same runoff model. So we'll go to General, and we will choose curve number. That should be about the same. Well, it is the same model. And the curve number in our prior example, I think it was 80. Let me check real quick here. So 85 is used in the HEC-HMS model that's pictured here. So I'll use 85 and hope that that actually works the same. Choose OK. So we're now almost the same. The remaining difference is if this is 15,000 feet, that's probably about 7,000 feet. And a good approximation for overland flow, if you're just kind of pulling stuff out of your datum, is about a mile an hour, which is 1 to 2 feet per second. So we may have to jack with the slope a little bit to get the times to be the same. Let's go ahead and, let me go ahead and save this because we haven't crashed yet, which is kind of unbelievable. I'm going to return to HEC-HMS, minimize it. Let's go ahead and get my rain gauge. And now I need to find the time series to load into it. I'm just going to give it that name for now. Hopefully it will let me move things. Oh, that's going to stay in the way. So the time series is contained in the HEC-HMS models. And it was that data that we processed already. I think it's in 0603. 15-minute rainfall. That's cumulative depths. So we want to copy all that. And we will paste that into that column. And now we have to get the time values correct. So that's every 15 minutes. So that's 0, 0.25. As long as we leave the date column empty, we can use fractional hours like I'm doing right here. At least you used to be able to. And so on. It doesn't have a fill feature, so let's go ahead and build the rest of that as needed. So we want to do a sequence from 0 to how many hours? 24. It doesn't look right. So we have to prepare the data in such a way that we can put the two columns together. So let me see if I can do this first. I think if I do I'm gonna take it out of the HEC-HMS because it's already formatted there. The challenge is working in rows and columns. I'll take my time series and take the time. So I really just want this column. Copy. Paste. Okay, so that's looking correct. And then we will go take the copy all that, paste, and we should be able to sometimes the last one, well, looks like we no, it didn't do it right. Let me try this again. No, I don't want to save. So the next thing we're going to have to manually do is deal with it going to the next day. Do this a different way. We will take month 1/1/20. So both these programs are actually a lot easier to use if you have prepared your data ahead of time. On the other hand, if you're doing this with billable hours, we're actually spending a lot right now, which would be very desirable from a business perspective. But there's nothing lost doing it the hard way for the time being. So my preference with SWM is that I actually can do this as fractions of hours, leave this column blank, and then go back and put the dates in later. Okay, so now we're at the new day, so it's going to be month, day, year, 1/2/20. Copy that, paste. Get rid of this other junk down here. Hopefully we have a good time series. Alrighty, that took a while, but there we go. We have our example, same storm. It looks like we expect it to. Choose OK. But I need to tell it that that was cumulative. I need to tell it that that was every 15 minutes. No, that's not the same. Let's save that work so that we don't have to lose it. All right. So now I think we are ready to attempt a simulation. We got it set up as close to the same things as we want. We now have to fix the dates to agree with that rainfall. We'll go to 1, 2. We'll go to 2,300 hours. I think that will work. We'll know in a minute. Leave the time steps into 5 minutes. 5 minutes. Outfall's been established. We've made the connection. We're using runoff curve number to convert rainfall into runoff. The area's been established. We made a good approximation for the width of that runoff plane. We have a rain gauge here. So what could go wrong? Okay, that was amazingly fast. That's usually scary. Let's take a look at the subcatchment and see what happened. Yeah, produced absolutely no runoff. Let's check that the rain actually produced rainfall. It's not even an option. So we'll go back here. Let's see if we even got precipitation coming in. That's the usual failure. I believe I just crashed the software. Yeah, we lost control. Oh, there we go. So we'll restart it and pick up from where we left off. File, reopen. One 120. I think I made a mistake in the timing. 120. Check the report. So whenever it's dealing with the timing, both softwares, all software that involves time is the same, because for some asinine reason over the years, we have insisted as analysts that it be in calendar time, which generally makes it impossible to figure out what's going on. One 120, 1 220. So there's nothing in, nothing out. The rainfall's not coming in correctly. I have a mistake here. Month, day, year. 1/1/20. Year. it's always, it's not picking up the time correctly, which is how professional programs work. That's what generates a lot of billable hours. I'm quite frustrated because we're trying to do this in a shared environment, and I didn't want to spend time walking through everybody's install because there was no way to debug it. Let's go ahead and rebuild those input files really quickly. I'm going to do them here on my local computer because I can get everything into 2 columns like I want. It is. No, it's not 2. Alright, so we get some Ash Creek up and running. It should be perfect. Use this. So there's what I want to put into that. Wow, everything's broken today. This was what I thought I wanted to put into it, but well, that's real data. I shouldn't be upset. And when this occurs to you all, you shouldn't be upset either. Delete all that. She's okay. This one, text to columns. Too much. Okay, this is a comma delimiter, right? All right, that looks like that's the data I want to move. So the file, I'll get that into an ASCII file. That'll work. File, save. Wait for it. Now I got to move it to the server. Go away with that. Don't save that. You have to go through Jupyter Hub, which hopefully is, we get all this stuff out of the way for the time being. I don't want to okay. So that's my remote Jupyter Hub. I need to find a local one. I don't have one. Maybe I have it running here. So this is the same as moving files through Moodle, except it's a little faster. So I want to shrink that, and then now I need to find the file, which had something. What part of close don't you understand? And then we go to find data file. There it is. Put it right there. It's uploaded. We'll return to shared site. Actually, I might as well open it because we're going to need it. All right, there's what I want to put into my Heck HMS. Excuse me, my swim. And as usual, the scroll isn't going to function. Copy to the clipboard. Now, with a little luck, we should be able to build the rain gauge. It's just not working at all. Okay, so let's just edit everything. So one of the things that what you're watching me endure right now, you're going to find in the next few years is going to be really common. There's a whole lot of change going on in the computer industry, both in the hardware and software. And some of our old stuff that we've been relying upon for decades is starting to break. And because this doesn't generate money for Amazon or Google or Apple or all that, there's not a lot of incentive for developers to maintain it. The person who wrote this program, they're my age. We're all getting old and dying, so it's unlikely that there'll be a major reporting. But with these compatibility layers like we're using here, we can keep them running for a little while longer. So cut all that out, so now that's empty. Be sure it took the cut. You see, notice how it's starting to lose the cancel that. We'll go back here. We lost the highlighting. It's interesting, it's basically two copies of the same file. That might be part of why it's not working right. Copy that. Rain. Paste. View. Oh, thank heavens. Okay. Close that. Save it. All right, now we are on what I think is elapsed time. So that was a little different. Let's see if we got rainfall. Yay. So here's our runoff once we've put the rain in. So my message here is, don't quit when it doesn't quite work right the first time. Even though the software is designed to save time, it usually doesn't. But once the data are organized correctly, then the tool is useful for our questioning. So let's look at the HEC HMS equivalent, and can't tell if I'm messing with sizing now so that I can sort of look at them at the same time. Oh, it will let me slide off the screen. That's actually kind of dangerous. So if you look at the picture on the left, there's subcatchment runoff, and in this case it's peaking at about 3,000 cubic feet per second. Here we have observations at 6,000, so clearly they're not calibrated yet. The black dots here, if you recall, are observed runoffs. But we do have the 1, 2, 3, 4 peak behavior, 1, 2, 3, 4. The second peak occurs a little bit before 1200 hours during the first day. So that would be 12 hours from the start of the simulation. In our SWMM model, it's appearing at hour 10, so 2 hours before the start. So while our timing is not perfect yet, it's reasonably close. And so at this point, we have a SWMM model and a HEC HMS model of the same watershed. Now, it's pretty arguable that the HEC HMS model was quite a bit easier to build. But with the SWMM model, we can now start to examine hydraulics. So that can go into a stream flow system. And HEC HMS isn't necessarily directly built to do that. The other thing of the SWMM model is that it's designed to work at the acre scale, so 5, 10, 15 acres, and we're at 4,000 acres. And then doing the same with HEC HMS to bring it down to the acres, you'd be at 1/640th of a square mile. So there's also a scale issue. But despite those two limitations, what we have is a fairly effective representation of the situation. Currently, neither of these would be adequate for modeling that watershed, but it's a starting point. Since I have you captive, let's see what happens if we make things wider. So I've just made the width artificially wide, which has shortened the distance to the outlet. And so what I expect to happen is these peaks will move to the left. Barely detectable. But now look at our flow rate, 6,000, 6,000. Again, that was hardly a calibration step, but the magnitudes, this is 2,500, this one's, a little under 2,500. The magnitudes at this point are the same. And if that's all we were after, I suppose you could just use the SWMM model as is. The next steps would be to incorporate things like evaporation and different kinds of losses. Evaporation, I believe, is a climatology feature in SWMM. And so we would provide evaporation rates, and in the case of SWMM, you provide them either in the climate file, averages, or temperatures. Or you can just put a evaporation rate per day. We supply wind speeds, and that's going to use internally an aerodynamic model for evaporation. Temperature, various adjustments. Aerial depletion, so that would be for snow, and snow melt information. So the climatology behavior in SWMM, arguably the inputs are straightforward. We'd have to do some reading to understand which of the models that it's using. I will expect that because it's not asking for latitudes anywhere, that it's directly incorporating something like a Penman-Monteith model to do the evaporation based on this other climatological information. In terms of infiltration models, that's built into the subcatchment hydrology, and we started with a curve number, but we could change it to something else. We do that in the options tool. In general, we could use modified Horton or green amped, or modified green amped. The difference between the regular and the modified is usually a storage term between time steps. So that's our introduction to SWMM, and I stipulate that with some knob twisting, we can make both computer programs produce nearly identical output. And in the HEC HMS, there is conceptual comfort in doing that because it uses a hydrograph model. In SWMM, there is a conceptual discomfort because we're having to produce a physical model that doesn't make physical sense in order to replicate the output. That doesn't mean SWMM's useless. Because we're not using unit hydrographs in SWMM, the better way to do this would be to break that watershed into a collection of much smaller sub-areas and then use hydraulic connections to route the water from that sub-area to the outlet. And in the extreme, if each of those sub-areas is an acre, we'd have 4,000 little sub-areas on that. It would very much replicate the hydrologic behavior that we observe. So that concludes the second example for SWMM. Let me save it so it's not broken. There we go. The second example for SWMM. I will move those files to the class server, so if you want to run them yourself, you can. And then tomorrow we're going to start with unit hydrograph, and actually I'm on my local thing, it's of no use. I want to be sure everything's there so that you can take a look at it. File, new tab. Give you some reading to do for tomorrow, or at least take a look at some stuff. Teaching. As usual, I can't see anything. Okay, if you take a chance before tomorrow, read or at least glance through pages 200 to 241 in Chow, Maidment, and Mays. It's up to you if you want to look at this highway hydrology. That can be pretty easy reading, actually, but the layout is kind of frustrating. You might want to read Sherman's stream flow from rainfall unit graph method from the 1930s. And a former colleague of mine, Dr. Leanhart, did quite a bit of work in unit hydrographs in the 60s and 70s. And both these are actually, in my opinion, really good explanations of the relationship between statistical mechanics and observed physical behavior. And then there is a the lesson's already there. You could take a look at that ahead of time, and I will get it coded into the Moodle site as soon as I can. And I don't think there's any examples for that. So tomorrow is pretty much a theoretical lesson. And there are some Excel files. There are some R scripts. These will make more sense when I'm actually doing the lesson. And I thought I had videos already. I'll have to go find out where the videos are. I have some pre-built videos, and then we will capture things tomorrow. So if there's no particularly burning questions, that's all I had prepared for today, or had intended to do for today. And you've now been introduced to the two softwares, HMS and SWMM. You're certainly encouraged to use the HydroShare site to run them, because then you don't have to do any installs. But as you can see, the network lag time is just enough that it makes you think things aren't working. And there's no equivalent to Excel on the remote server. So, and it's actually a useful lesson, is that it goes much easier if the data are prepared in the right structure ahead of time before you try to load them into the two software packages. And we all get lazy because we get working on our laptops and we get used to it, and then trying to work in a different environment is a little bit humbling. So with that, that's all I have for today. Please take a look at exercise set 2. Try to get it done by Friday. If there's questions on it, certainly bring them up in tomorrow's lesson. It's fairly straightforward. So you're applying Thornwaith and Blaney-Criddle to 3 different locations in Texas. And those locations are selected because through the remainder of the class, we're going to have study watersheds in those areas. And so we're going to want that information ahead of time for applying our different surface water hydrology conceptualizations to those areas. So rather than have to go look it up at the time, once it's done, we have all the tools in place. So with that, I'm going to terminate the video. I'm curious, Superada, where that photograph is from. I mean, it looks like a train somewhere in a turn. Where in the world is that? Oh well, can answer some other time. I have pictures of myself in trains all over the world, kind of like almost the same picture setup. Okay, well that's all I have for today. If there's no questions, I'm going to go ahead and stop the call, and I will see you tomorrow, same bat time, same bat channel. Everybody good? Excellent.